Hi friends, in this video we are going to see some sources which we call as power sources or energy sources. So there are two types of sources. Voltage source and current source. As per the connection of internal resistance, voltage source can be further classified as ideal voltage source and practical voltage source. Here also for current source we have two types. Just like a voltage source, it is ideal current source and practical current source. So let's see all these sources one by one. So let's start with the voltage source. So I am having one voltage source like this. To this voltage source, I am connecting a load resistance RL. Now in this connection, there is a closed path, so current will pass. Current flowing through RL will denote as IL, and because of which by Ohm's law I will get a voltage across RL denoted as VL of this polarity. Now if you see properly, this VL will be nothing but V, which is a voltage supplied by this voltage source. Basically, no matter whatever value of resistance we are having, still VL will be equal to V. That means VL is independent of RL. And hence it is independent of IL. Suppose I want to draw the characteristic of this voltage source. I will keep on increasing the value of IL, but still VL will remain absolutely same, and that is equal to V. This is called as ideal voltage source. Its voltage is independent of IL. Let's see its counterpart, that is practical voltage source. So practically the voltage source is like this. A small resistance will be in series, and to this I am connecting a load resistance RL like this. Once again, this circuit is closed in order to pass a load current IL, which will develop a potential drop across RL, which is VL, of this polarity. Now definitely over here VL will not be equal to B, but it will be less than V. Why so? Because this RSC will come into the picture and some drop will happen across this. So if I want to write the equation of this VL, that will be V minus IL RSC. Now my VL depends upon IL because IL RSC is a voltage drop across RSC. Suppose I want to draw a characteristic of VLIL for this type of source. Had it been RSC is not there, just like the ideal voltage source, the characteristic will be like this, which I call as ideal voltage source. But because there is a RSC, there will be some drop in the VL and the characteristic will have a drooping nature for this, which we call as a practical voltage source. And this drop is nothing but IL RSC. So this is the VI characteristic of a practical voltage source. This is the VI characteristic of ideal voltage source. Now the question is that, suppose I am claiming the voltage source is giving a particular voltage. We cannot afford to get a very less voltage compared to the given or specified by the manufacturer. Meaning, we cannot neglect this RSC, but while designing, we have to make sure that this RSC should be as low as possible. What is the RSC? RSC is nothing but internal resistance of the voltage source. Ideally, what should be its value? It should be 0. So, in ideal voltage source, RSC nothing but internal resistance of the voltage source is 0. So 0 resistance means that condition is a short circuit. So in ideal voltage source, resistance, which we call as the internal resistance of a battery or a voltage source, is having the value 0, but practically that RSC will be present, but that should be as low as possible. Let's go to next source, that is current source. So here I am having a current source like this, current I. These are the points A and B. To this current source I am connecting load resistance RL. So once again circuit is closed, there will be a load current IL which will develop a load voltage VL across RL of this polarity. Here it is obvious that load current equal to source current. So IL equal to I. No matter what is the value of a load resistance, still IL will be equal to I. So what does that mean? This is independent of RL. Hence, it is independent of VL. Let's draw VI characteristic of this current source. Since it is independent of the VL, it will have the characteristic like this, having a constant value of current which we call as I. It is called as ideal current source. Let's say its counterpart, that is practical current source. So practically, current source is represented like this. There is a resistance in parallel or in shunt, therefore it is denoted as RSH. To this I am connecting a load resistance RL. These are the points A and B. Here also load current will pass, developing a potential drop VL across load resistance of this polarity. Now I is having two paths, so definitely some amount of current will be passing through this, which is ISH. So this time it is very much sure your load current will be less than I, and that is less than I by this amount. Now RSH and RL are in parallel, hence voltage across them will be VL. So I can write this IL is I minus VL upon RSH, because we need to draw the VI characteristic of practical current source. If RSH is not considered, it will be an ideal current source like this. But because there is a RSH, the practical current source will have the nature like this. And this drop in a current is VL upon RSH. What I want, a maximum current should pass through the load resistance. That is the aim of the current source. Meaning ISH should be as low as possible, and that is possible if this RSH is very high. So internal resistance of a current source is as high as possible. Ideally, that should be infinite. So in ideal current source, internal resistance is infinite. And infinite resistance is nothing but open circuit. So this is all about a current source. Let's go to the next part. Now, in a problem, we are supposed to reduce the network. Resistances could be reduced by series parallel, star delta. In order to reduce the sources, we need to see some different strategy, and it is very simple. So first, reduction of voltage source. Whenever voltage sources are connected in series, we can reduce them. See how. So in first part, I am having voltage sources connected like this. I will say this is V1, V2, plus minus, plus minus. Let's take these are the points A and B. This implies it is a series connection of voltage sources, and we can add them up to become a one source of the potential V1 plus V2. Why it is a series connection? Because different polarities are tied together. So that connection is a series, and voltage source will have the value V1 plus V2. Similarly, I can have like this. This is also a series connection because positive of a one voltage source is connected to negative of another voltage source. So this also implies a series connection giving you a equivalent voltage of this polarity. Its value is V1 plus V2. So this is a simple thing. Now let's go to the next part. Sometimes it may happen that negative polarity of one voltage source is connected to negative polarity of another voltage source. So like polarities are tied together at that time, this is called as a series opposition. Series opposition means we need to subtract two voltages. So here I am considering V1 is greater than V2. So V2 is subtracted from V1, hence I will get the resultant polarity same as V1, and the magnitude of this resultant voltage source is V1 minus V2. Like that you can have four combinations. So suppose here positive is connected to the positive of another source. So basically what we have to remember is like polarities of voltage sources if connected together, then I can say that is a series opposition. Once again I am assuming V1 greater than V2. So resultant voltage will have the polarity same as V1, and the magnitude will be V1 minus V2. Same thing you can write if you are considering V2 is greater. So this is all about reduction of voltage sources. Let's go to the next part, that is reduction of current sources. Let's go to the reduction of current sources now. Here also we are having two types. In first place, suppose current sources are like this. This is I1, this is I2, A point, B point. So here this can be reduced into a one current source given like this. And the value will be I1 plus I2, because these two current sources are in parallel. Same way, if you are having current sources like this, both are contributing current in the same direction, and more important, it is contained parallel between 2 points only, then I can say resultant will be like this, and the value is I1 plus I2 once again. Whereas in second case, they will be in opposite direction. So for example, Suppose this is I1 and this is I2. See, important thing is that both the current sources are connected between 2 points, and I am assuming that I1 is greater than I2, then resultant will have the current direction same as I1, because we consider I1 is greater and the magnitude will be I1 minus I2. You can write this because these two are in anti-parallel. Anti-parallel means these are connected between 2 points but in opposite direction. Likewise, you can write for I2 and I1. If you are having a different directions of current, those are anti-parallel. Subtraction of current sources should be done. Whereas if they are in same direction, then we need to add both the current sources. This is the thing required in order to reduce a complete circuit into a single source and single resistance, so that by Ohm's law you can get a current flowing through that particular resistance. Thank you.